Thank you, Inaki. Thanks very much to the organizers for setting this up. I guess it's been 6 years now since the trimester program. I was here with a group with Leonard Meyer. Leonard's there, yeah. And Akil Matthew and Rosona Eldred, and we were doing mostly periodic unstable homotopy theory. And I think for us it was a very productive time. We learned a lot, and this stuff is in some sense still a continuation of that. With different people, but okay. Okay, yeah, I wrote their names, but it's part of a larger joint project with Lucas Bruntner and Jeremy Hahn and Alan Yuan. So let me first recall some sort of classical statements about exponent results, and then try to explain how to attempt to generalize that. So first results here are for p in odd prime, or originally it was in p at least 5, but so there's some work of Cohen, more Neisendorfer, and then just Neisendorfer in the late 70s, early 80s. And what they were doing is they wanted to prove exponent bounds for the p primary torsion in the homotopy groups of Moore spaces. So at first they didn't quite succeed, they did it for spheres instead. But then later also Neisendorfer figured out how to do it for Moore spaces. So for example, they proved the following result. If you look at the homotopy groups of a mod p Moore space, something like sk mod p, or maybe mod p to the r for some r, then these have a bound under the torsion, right? I mean, at first it looks like a stupid question because you've modded out by p to the r, but of course co-fiber sequences don't play well with homotopy groups, so it's actually not at all obvious that this has an exponent, but it does. So these are annihilated by, not by p to the r, but by p to the r plus 1. Actually, I proved something slightly stronger, or Neisendorfer, I guess, proved this. He proves that the space, so there's a geometric version of this result. The space, which is the double loop space of this thing, this actually has an exponent in the geometric sense. So, right, I mean, this is an H space, sorry, plus 1. You can add the identity to itself, p to the r plus 1 times, and you get a null homotopic map. And then later, Therio worked at the prime 2, and using somewhat different methods, was able to mostly settle that case. So you also get an exponent when p is 2 and r is at least 2. And apparently the case of the mod 2 Moore space is still open. So if you were looking for some problem, this is sort of, oh, I don't know.
One question. I think it's surprising that PR is within independent of the star. Maybe I'm late.
Well, that's the right. I mean, if you look at any fixed homotopy group, then it's not so hard to deduce that there must be a bound on the p torsion. That the bound is uniform in star. Like that's the key point.
Yeah. For spheres,
for spheres, it's right. For unstable spheres, it's true, right? The homotopy groups. If you take the homotopy groups of something like S2n plus 1. And you forget about the z, then this is annihilated by p to the n.
Oh, sorry,
yeah, I mean the stable homotopy groups of spheres don't have a bound, but the unstable ones have one that grows exponentially in n. Yeah. So that's actually what Cohen and Neisendorfer first proved in their paper, and then those methods were then also extended to this case. Yeah. So this also has a bound. Yeah. For odd p, right? Yeah. For p is 2, it's I think the sharp bound is still unknown. I mean, there's a conjectured bound by Mahol. Yeah. Right, so what about generalizing this? So what I want to talk about today is versions of results like this where you don't only look at p exponents, but other kinds of exponents coming from chromatic homotopy theory, so things like VI exponents. Right, so according to chromatic homotopy theory, or more specifically the fixed subcategory theorem, finite spaces, finite CW complexes can be organized according to their type. Right, so if you have a finite space is of type 0, X is of type 0. Well, if it's rational homology, does not vanish. And of course, if you have such a space, then you shouldn't expect it to have any exponent at all. If the rational homology doesn't vanish, then there's not going to be a power of p that annihilates it. Right? So this does not have any exponent. For these kinds of spaces, you're not going to prove anything. Now, a space is of type 1. These Moore spaces are going to be examples if, well, the rational homology vanishes But if you look at the mod pk theory, right, I could have just written k theory actually. So say mod p complex k theory of x is non-zero. Okay, so Moore spaces are examples of such spaces, and these generally you would expect these to have p exponents. Right, so I mean the space is rationally trivial, so at least it's p torsion, but you somehow would like to exploit the finiteness of the space to prove that it really has a global bound on the p primary torsion in its homotopy loops. And this is something that you can continue. So
this is not known.
This is not known. No, it's only known for Moore spaces. Where are you? I mean, oh, there. Yeah. So generally, the space is called of type n if you look at the reduced Moravec K theories of the space, and these are 0 if I is less than n. So this is non-zero if I is n. And, well, for example, the Hopkins-Smith periodicity theorem tells you that if you have such a space of type n, then it's also going to admit a Vn self-map, at least after appropriate suspension. So any finite space of type n admits after appropriate suspension what's called a Vn self-map. So this is a map from some suspension of the space to itself, which induces an isomorphism in this nth Moravec K theory. Right, so this is the periodicity theorem of Hopkins and Smith. That's part of that. Okay, so this gives you a recipe to sort of create type n+1 spaces out of type n spaces, because if you had a type n space x and you had one of these self-maps, you could take its cofiber to kill the nth Moravec K theory. Right, so the cofiber x mod v is then of type n+1. So this gives you sort of an inductive recipe to, well, it's not a, you only get existence out of the periodicity theorem, so it's not really a constructive recipe, but it gives you a sort of recipe to think about these spaces of higher type. So you can use this to sort of inductively construct spaces of the form you start with a sphere, and then you mod out the power of p, say R0, and now, according to the periodicity theorem, this admits some V1 self-map, which I'm just going to call V1 to the R1, so indicating that it acts in some way in BP homology, but whatever. And then, well, once you've modded this out, this will be a type 2 space that admits a V2 self-map, and you could mod it out, and et cetera, et cetera. So you could continue like this up to n, and sort of construct spaces of this form. And this is, well, you might always have to suspend in the middle, so k has to be large enough for these powers to be appropriately large. And these kinds of spaces are the generalized Moore spaces from the title.
Are these singled out like not by construction but by property?
And what's the property?
This is the question.
This is the question?
Yeah.
Well,
type whatever n+1.
Well, I mean, not every type n spaces of this form.
Exactly. So
Type n.
you never recognize.
How do you do it for ordinary Moore spaces?
This like a connected space whose homology is concentrated in one degree.
Yeah. So okay. So the reason these are called generalized Moore spaces is, I mean, they don't look like Moore spaces from the point of view of ordinary homology, but they look like Moore spaces from the point of view of BP homology. Right? Their BP homology looks like what's suggested by this formula. So in that sense, they're Moore spaces, and I have to think about if they're really characterized by that. I would think unstably, definitely not. So I'm not sure I want to, yeah. try to characterize this class of spaces. Also, actually, I'm just using these spaces for expository purposes. The thing I want to prove is going to be for a general type n plus 1 space, so it doesn't really matter. I just wanted to contrast this with that. And if you write a formula like this, then also a result like that strongly suggests that this should have, well, first of all, something like a p exponent, but it should have many more kinds of exponents. So that's the rough guess here. I don't know. I looked through the literature a bit, but I couldn't find an explicit conjecture in this direction, but I'm sure it must exist. So you could guess that a finite space of type n, let me make these n minus 1, so they're really justified in type n. So a general finite space of type n should have exponents, so it should have a p exponent, but also well, vi exponents. I'll explain in a minute in more detail what that means precisely. Vi exponents for I less than n. Okay. So the goal for this talk is to explain why some version of this is true, but it's the thing I'll attempt to explain is a weaker form of this result. So this is essentially true. I mean, I'll have to include a few extra hypotheses, but I'm only able to show it after inverting VH for arbitrary H. And so you can choose H as large as you want. You probably want to choose this very large. Okay, and I'll also try to explain what this means exactly. But so what it's saying is that once you disregard sort of VH torsion for very large H, then at least on the remainder of the homotopy groups you get these kind of bounds. The reason that this doesn't apply something like that is that I can't make this uniform in H. If you could, then you'd be quite far in proving something like that, but I don't know how to do that. I don't even know if it's true. Well, if I knew it was true, then all right. Okay, so let me try to explain a bit more precisely what these sort of vague statements mean. Okay, so first of all, I should really define what it means to have a VI exponent, right? So let's just fix a pointed finite space of type I, and also let's assume it comes equipped with a VI self-map. Okay, then for a general X, so a pointed space X has a VI exponent if the following system of maps is nilpotent. So you could look at the space of pointed maps from V into X, and then pre-composed by this little v, and that would land you in default loop space of that thing. And you can continue, you would land in the 2 default loop space, etc. And I just want some number of composites of maps in this system to be null-topic. So this system is nilpotent. Okay.
Sorry, the order of nilpotence will depend on the map V that we choose, right?
Yes, I'm only going to talk about the property of being nilpotent, but not about the actual exponents. Of course, you could try to fix choices so that you can define exponent. We're never going to be able to, currently at least, to calculate any of those anyway, so I'm not going to bother to... So it's really going to be a qualitative result. Yeah. I mean, also the proof will be sort of non-constructive in a way, so you're not going to get actual numbers out like you would for Cohen or Neisendorfer, as we'll see. Oh, I should also say, of course, the way that I wrote the definition, it seems to depend very much on choices, capital V and little v, but yeah, I mean, the fixed subcategory and periodicity theorems will imply that that's not the case. This really only depends on I, this property of having an exponent.
So, as somebody explained earlier, you could also ask that it's 0 on pi 0 instead of being I.
Yeah.
Is that something that you would do or not do? Is that, I don't know,
well, if I don't have to, I'd rather not. Like, I mean, I know how to prove it in this form, and I prefer this form over the one that you suggested. Of course, if you could only prove that one, then you'd go with that one.
So you say it's not a relevant question somehow.
Well, it is relevant actually. There are cases where, so for example, there's this very strange result. So Gijs and Wang proved that if you look at the homotopy groups of S3, well, like the V2 periodic homotopy groups, so you apply the second Gaussian-Kuhn function, and you prove that V1 squared acts trivially on that. Like, I mean, the homotopy groups are P torsion, so there's a well-defined V1 operator, so it squares to 0 on homotopy groups, but not geometrically. The actual spectrum doesn't have a V1 exponent, so there is something funny going on there, where you have this algebraic exponent, but not a geometric one. So it's not stupid to distinguish between the notions now. And in that case, I mean, yeah, he was only able to prove that algebraic one, and you just provably can't upgrade it. But I don't know what to make of that. Right. Other questions on that? All right. So maybe just a quick comment. I mean, I don't want to only consider exponents for things in spaces, but this is, of course, a definition that you can make quite generally. If you see some infinity category with finite limits, then you could always define, you have an object x and c, you can define x to the v as usual, just to be the limit over the constant diagram indexed by v of x, but v is still finite space type I, and then you could look at the system x to the v to loops v, x to the v, etc. like this, and also define what it means for x to have a vi exponent in this context. So that's sometimes useful to do. All right, so that's what exponents are, and then I also have to tell you what it means to invert VH. Okay. Okay, so essentially what you want to do is you're looking at the category of pointed spaces, and out of it you want to create a homotopy theory in which VH self-maps are equivalences. So you want to localize in some way. So if VH self-maps are supposed to be equivalences, then at least the cofiber of any VH self-map should be contractible. So that's the place to start. You can say, okay, well, the cofiber of a VH self-map, that's a type H+1 complex. Those things should die in that localization. And it turns out that's essentially all you have to do. So what you can do is the following. So you can fix just a finite space, let's call it F, of type H+1, and for technical reasons you should assume it's a suspension. Let's not worry about that very much. Then what you can do is you can localize, so you can form the Bausfield localization with respect to the map that just kills F, so F to the points. Like this is the map that you sort of universally want to turn into an equivalence. And so this gives a localization functor, which I'll denote by LHF. The F stands for finite. And it turns out that this localization has more or less all the nice properties that you would hope for. This behaves much better than maybe so let me introduce one piece of notation. So I'll write D for the dimension of the bottom cell of F, the first non-vanishing homotopy group, and I'll define, use the following notation, LHF of pointed spaces. and then D connected. So this is for the full subcategory of this localized thing. Full subcategory of pointed spaces on the D connected LHF local spaces. I mean, it's just for technical reasons that you have to sort of throw away the bottom few homotopy groups, because this localization with respect to such a space is never going to affect homotopy groups in dimensions below the connectivity of that space. So then Bausfield proves the following. So he shows that this, well, does exactly what you want it to from the point of view of chromatic homotopy theory. So he shows that a map X to Y of D-connected pointed spaces is an equivalence with respect to this localization. So it's an LHF equivalence if and only if it gives isomorphisms on periodic homotopy groups up to height h. So if it induces isos on VI periodic homotopy groups for I less than or equal to h. Okay, so if h was 0, this is really just rational homotopy theory. It's saying a map becomes an equivalence for this localization if only if it was a rational equivalence. And for higher h, you're keeping track of more and more of the chromatic layers. So you're taking into account the first h plus 1 chromatic layers. All right. So this, if you wanted to, well, if you want to do unstable periodic homotopy theory or whatever, then like this category is your friend. It's the place to work. Okay, so let me just state a few basic facts that are relevant for the proofs at least. So first of all, this localization from D-connected spaces to these LHF local D-connected spaces, well, it preserves co-limits. That's true of any localization of this kind. But it also preserves finite limits, and that's, well, that's not at all obvious. Like it's a theorem you have to prove. And then also, let me just state, without making this much more precise, but this localized homotopy theory, it admits good Willi calculus. So all of the usual arguments from, say, good Willi 3 apply in this category. And that's relevant in the proofs. Okay. Right. So now let me at least state an actual result.
Can I ask an easy question?
Yeah.
So why can I can also just do some kind of a Hausdorff localization with respect to this map B?
Yeah.
Is that the same as killing that co-fiber kind of thing? So
Almost. I mean, it's
because it's unstable, so this is why I'm good.
Yeah. No, I mean, it's a good question. I mean, in some sense, that's the nicer thing to do. And you can state a similar theorem, you have to state it just marginally differently. It's almost the same, but it turns out that, well, doing what I just described is actually good enough, so I'm going to stick with that. But you could do what you described now. But you have to be a bit careful about, for example, this. You run into some sort of iffy things exactly around this connectivity dimension that you have to,
But
like the bookkeeping is a bit, yeah.
Does this guarantee that now little v is an equivalence in that category?
Yeah.
I see.
It does. Okay. Right.
Guys,
Yeah.
perhaps I've missed it, but why does LHF preserve deconnected spaces?
Yeah, that's not obvious. That's, again, something you have to prove. That one's not very difficult. Like, that one you can take as an exercise. But it's a good question. There is something to prove there, but it does. And it's specifically D-connected. It doesn't deconnected, sorry. It's specifically for D, not for other. If you had something that was very highly connected, then usually LHF localization is going to bring it down in connectivity. Yeah, thanks. All right. Here's the main result. So essentially this result is going to relate the stable and the unstable exponent of the space. That's the whole point here. So if you have a deconnected space and you have sort of a stable exponent for it, so you have exponents on its suspension spectrum or maybe its localized suspension spectrum. So let's say that LHF of sigma infinity x, where now LHF denotes the corresponding localization but in spectra, so that this has a VI exponent for all, let's say I less than some fixed number n. Then, well, the thing that I would like to say is that x itself, or the LHF localization of x has this. Can't quite prove that, you have to suspend once. So, and so does the space LHF of the suspended of x. So at least if you suspend x once, then you get all these exponents. Okay, so in particular, this will apply to the spaces that I described in the beginning. So,
There's an H and an N.
yes, correct. And they're independent of one another. Yeah, you might want to choose H much larger than N, otherwise, or at least N, otherwise it's not going to be very interesting. Yeah. So this H is just some auxiliary number which you want to take to be very large. So in particular, this applies to X, finite, and type N. Okay? Because if you have a finite type N space, then its suspension spectrum that's a finite type N spectrum, that will have these exponents just by the periodicity theorem. So that part, well, I'm not going to say it's easy because you need the periodicity theorem, but that you have, and then this theorem allows you to lift it to the space itself. I'm not claiming that these exponents would be the same. I mean, they're very much not. But at least you get this implication. All right. Okay, so let me use the remainder of my time to at least give an outline of a proof, or at least set some of the ingredients of a proof. So there are really two parts to this. So part A of the proof, well, you could summarize it by the following slogan, I guess. So the slogan is that H spaces in this category LHF of spaces are homotopy nilpotent. So I'll specify this more precisely, but what it means is that they have a convenient finite resolution in terms of infinite loop spaces. So let me first state the corresponding fact in rational homotopy theory, which might be familiar, and that's the fact that we're generalizing here. So if you have a rational H space, then actually it's also an infinite loop space. Or actually, I mean, in this case, X is a product of Eilenberg plane spaces. Well, any rational infinite loop space is that. There's one little thing to be careful about, like the infinite loop space. I'm not saying anything about the compatibility of this structure with the H-space structure. It's just the underlying space of it. Forgetting the H-space structure, the underlying space is an infinite loop space. Another way to say this is that if you look at there's always a canonical map from X to an infinite loop space, namely this one. And if X is a rational H space, then this map admits a retraction. And it's just an equivalent way of saying the same thing. Okay. All right. So, in other words, like if you were thinking about rational homotopy theory in terms of Lie algebras, then this would be like saying that any H space or any H object in rational Lie algebras is in fact abelian as a Lie algebra. So that's the fact that you can generalize to periodic homotopy theory. Let me introduce the relevant notion here. So let me call an object nilpotent So let's say an object is homotopy nilpotent, maybe of exponent k, if, well, I'm not going to use this map, but I'm going to use the higher stages of the Goodwillie tower of the identity. This is really the linearization of the identity function. It's P1 of the identity. But you could look at other PKs. So I could look at X going to PK in the sense of Goodwillie, so the K decisive approximation of the identity applied to X. So if this admits retraction. Okay. So this notion of homotopy nilpotence for a space, it's very close to the one that, for example, Biedermann's wire considered.
Will you explain why this is called homotopy nilpotence?
Well, it's by analogy with ordinary nilpotence, but the point of this, I mean, I think the terminology is Biedermann's wires also. So what they do in their paper is they compare the Goodwillie tower of the identity to the lower central series construction that you get up like the Conley group. So those are not the same, but there's a map from one to the other, which actually rationally does become an equivalence. So it's sort of, in that sense, the Goodwillie tower is analogous to the lower central series, and for the lower central series, like this would be like really nilpotent as a group. So it's like a homotopy version of that. Yep. Right. My board use is becoming less efficient. I feel like I'm doing a lot of
Does it imply that you have a finite limit of infinite loop spaces?
Yes, it does, because retract is
right? That takes. I'm confused about that.
well, I mean, the Goodwillie tower is really, it's a tower of principal fibrations where all the classifying maps are infinite loop spaces. So the Tates are not going to play a role in that. No.
Well, but then the things you pull back have homotopy orbits. Don't they?
Yeah, but I mean, there's still infinite loop spaces, right?
That's true.
I mean, there are infinite loop spaces of a homotopy orbit spectrum. Yeah, exactly. Yeah. Okay, so the first ingredient that you need, which is called theorem A, is that any H space in this localized category is homotopy nilpotent of exponent P to the H. All right, so that generalizes the statement from rational homotopy theory where you set H to be 0. You're saying it's homotopy nilpotent of exponent 1, that's saying it's a retractive Loops infinity sigma infinity. All right, so I don't really have the time to go through an actual proof of this, but let me just say what the ingredients are. So I think the most important ingredient is the theorem of Baron-Mahold, which says that spheres, or odd spheres, after LHF localization are nilpotent, homotopy nilpotent of this exponent. Okay, so for odd spheres, you know how this works by Baron-Mahold, and then this being homotopy nilpotent is preserved by taking a loop space. It's also true for loop spaces of spheres. And now you can try to get to loop spaces of wedges of spheres using the Hilton-Milner splitting. So the Hilton-Milner splitting allows you to deduce this essentially to get to loops of wedges of spheres once you have it for these, there's a sort of an argument you can make extending by sifted colimits that will tell you that it will work for any loop space. And once you know it for any loop space, you know it for any H space, because any H space is a retracted loop space. Okay? So these are the steps, but there's a few bumps that you have to navigate while you're trying to really carry out these steps, but that's the main point. Okay, so that's the first half of the proof, so to speak, and part B of the proof is, it's a little trick about polynomial functors and exponents. You can just call it theorem B, maybe. So it's a trick that I learned from Akil. It's still here in spirit. So here's the trick. So if you have a polynomial functor, let's say from spectra to itself, and the result is more general than this will suffice. So if this is a reduced polynomial functor, and you have a spectrum, let's say y, that has VI exponents for all I less than some fixed n, then so does f of y. Okay? So if you think about it, it's very clear that exact functors will preserve exponents. That is easy to prove, but it's actually true for polynomial functors as well, not only for exact ones. Okay, so with these two ingredients, I can tell you how the proof of that main theorem goes. Right, so you start with an x, satisfying those assumptions over there. So we want to show that LHF of sigma x has these exponents. Actually, it will suffice to prove that for the loop space. Like a space has exponents if and only if its loop space does. I mean, the homotopy groups don't change. And look at the definition I gave of exponents, you'll see that this doesn't matter. So it suffices to show that LHF loops sigma x has the desired exponents. So now, by theorem A, well, this thing is a loop space in this LHF local category. So this thing is homotopy nilpotent. So it suffices to find exponents for the layers in the Goodwillie tower. I mean, we get up to a retract, we get a finite resolution of this thing into the first P to the H layers of the Goodwillie tower. So if we have exponents for each of those, then just by induction up the tower, we get it for the total space. So it suffices to find exponents for each of these layers. So we usually denote a dk of loop sigma x. So by definition, that means loops infinity of the kth derivative of the identity functor on spaces smash with, the suspension spectrum of this thing to the k, and then homotopy orbits. And I'm supposed to read this as first taking homotopy orbits and then loops infinity. Okay. So if I can get exponents for these layers, I know that this thing itself will have an exponent. So now, of course, we'd like to apply this theorem B. So to apply theorem B, we would need exponents for these things. But that's actually simple because this here, just by the James splitting, this would be LHF of the direct sum of, use a different index, J. Sigma infinity x to the J, like this, and this has the same exponent as x. So this has the same exponents as x. Sigma infinity x, sorry. or LHF of sigma infinity x. Right, if I take a spectrum with exponents and smash it with something, it will still have those exponents. Right, so that's the idea of this proof. Right. Okay.
Do you suspect that this, having to pass to the suspension of x is necessary?
I have no idea.
For the result to be true?
I don't know. Yeah. Yeah. I would like it not to be, but I don't know how to get rid of it. I mean, it's hard to come up with reasonable expectations because there's so little actual evidence, right? So, right, so also this proof strategy should make it clear why at least this method is never going to give you something that's uniform in h, right? Because the number of layers for which you have to find exponents grows exponentially with h. So it's sort of, you're never going to get uniform bounds on exponents by an argument like this. So, just a few minutes. So maybe I'll just use those few minutes to try to explain how you get theorem B. So should be able to do that pretty concisely. So, okay, so the theorem B, the proof of theorem B. Just introduce a few terms. I mean, this is not complicated, but it involves a trick that I thought was clever. It's not my trick, so I can say that. So let's say C is a stable infinity category, and F is a finite spectrum. Then I want to use the following terminology. So first of all, I'll say X in C is F nilpotent if it's in the fixed subcategory generated by things of the form F tends to Y for Y in C, right? As soon as if you have a stable infinity category with finite, it makes sense to tensor with finite spectra. Any stable infinity category is tensored out with finite spectra. And similarly, I'll say X is F torsion if it's a colimit of F nilpotentials. Right, so this F nilpotence is really some sort of finitary condition. It's built in finitely many steps from these kinds of things, and this is just usually something like a localizing subcategory generated by nilpotent objects. So why is this relevant to exponents? Well, there's a little lemma here. If you have an object X and C, this will have VI exponents for all I less than n, if and only if X is V nilpotent for any type n, finite type n spectrum V. Okay, so the proof of this is really just an exercise in the periodicity and the fixed subcategory theorems. So you can translate between having these exponents and being nilpotent with respect to these finite type n spectra. Okay, so here's another formulation of this trick of Akil. It says if you have a polynomial functor, so let this be reduced polynomial between stable and infinity categories, then this functor preserves F nilpotence. Okay, so whenever you apply it to an F nilpotent object, you get another one. All right. So the proof is, first of all, you reduce the homogeneous functors. So you reduce by induction on the Goodwillie power. And this P is going to have a finite resolution. By homogeneous functors. And then what you do, I didn't assume that P preserves filtered colimits, but you can always make it so by passing to the int categories. So you embed, so you extend P to a functor P hat from int C to int D that preserves filtered colimits. Alright, so you have to think about size a little bit, but actually without loss of generality, you could always work with small c and d, or you just choose your universes appropriately so that c and d are small. And then you can pass the int. Alright, so then, Goodwillie's classification of homogeneous functors will tell you what this looks like. So then Goodwillie calculus implies that actually this P of x must look like something like L applied to x, homotopy orbit sigma n for some multilinear L from int c to the n to int b. All right. So this is a functor which, in particular, this L is exact in every variable. So it's going to be very clear if you input something that's F nilpotent, then the result is going to be F torsion. So this P preserves, it sends F nilpotent things to F torsion. Okay, so this is sort of clear. But of course, that's not really what we're looking for. We're not looking to get something F torsion. We want something that's actually F nilpotent. Well, the whole point is actually what we've done already suffices by a sort of standard trick. Okay, so the claim is this is already enough. Alright, so if you start with a nilpotent thing, so if you have an F nilpotent object in C that is also F nilpotent in C, so then it's also F nilpotent in C, just because the inclusion of C into in C is exact. So this preserves nilpotent object, not necessarily torsion objects, because otherwise this proof is going to show that anything that was torsion was actually nilpotent, which is complete nonsense. Okay. So you have to be a bit careful. But okay, it's F nilpotent in C. So then, we get that P applied to X. It's F torsion. So in particular, you can write it as a big filtered colimit of compact F nilpotent objects. So this is a filtered colimit So compact F nilpotent objects. But also this thing, I mean, it's actually, this equals P of X. It's actually in the compact objects in D. So Px is also compact in D. Hence, it must be a retract of a term in the diagram. So hence, Px is a retract in D of a compact F nilpotent object. Okay, but then it's also F nilpotent when considered as an object of D itself. Okay, and that's the end.
So, sorry, is it, I mean, it's an F nilpotent of a filtered colimit of things, and it's F nilpotent. And how do you use a filtered colimit of F nilpotent compact things?
Well, if I have anything that's torsion, I can first write it as a filtered colimit of nilpotent things. I mean, anything that's torsion is a filtered colimit of nilpotent things, and then I can write each of those as a filtered colimit of nilpotent compact things, or I could do it in the other order. I mean, it doesn't. I mean, those generate the whole category.
Oh, yeah, sorry, I thought you wanted to reply this. Yeah.
Right? Okay, so yeah, that's, I'm done. Yeah.